So we discussed the impairments, the general impairments on an FM signal, and we will see how FM deals with those impairments, or what is the effect of those impairments on the FM signal. So the first type of impairment is nonlinearity. So a very useful feature of angle modulation, that is the FM and PM, the phase modulation and frequency modulation, is its constant amplitude, which makes it less susceptible to nonlinearities. So consider, for instance, an amplifier with a second order nonlinear distortion whose input is xt and output is yt are related by this expression. So nonlinearity generally comes from the amplifiers, which are required to amplify the FM signal before they are transmitted through the antenna. So in this expression, we have an amplifier which has second order nonlinearity. So the output is related to the input in this through this expression. So the first term here, this one is the desired term. So we want that a quantity, an amplifying factor, A1 is multiplied with xt, and this is the output that we desire. But unfortunately, due to the nonlinear nature of amplifiers, especially the high power amplifiers, we have other terms as well. So they cause nonlinear effects. So let's say if we substitute an angle modulated signal in the above expression, an angle modulated signal is generally represented by this expression, where we can see the phi t represents the angle modulation and the amplitude A remains constant. So we have trigonometric identities that can be used to obtain the output of output yt when the input xt is given by this expression. So we substitute this xt in the above expression. So the output is given by this yt here. So here we can see we have the higher frequency terms, 2 omega c, 3 omega c, and up to n omega c. How can we obtain them? So this has been done by using the trigonometric identity. So for example, cos square that we obtain here, cos square theta, can be written as 1 plus cos 2 theta divided by 2. So using this trigonometric identity, we get this expression where we have the higher frequency terms like this and so on. So omega c is generally quite high. It's in megahertz. So we can filter them out. We can remove the higher frequency terms, and we can filter only this desired signal out, right? So this can only be done if the input signal is an angle modulated signal. So this shows that angle modulated signals are generally immune to nonlinear distortions. However, if we have an AM signal, the amplitude modulated signal, it causes it gets distorted when we pass it through a nonlinear like a nonlinear component such as an amplifier. So let's consider a double sideband suppressed carrier signal, which is given by this expression. Let's say we pass it through a nonlinear response that is given by yt as axt plus bx cube t. So when we pass this, when we give this signal as input to this expression, we get this output expression. After rearranging this expression, we are left with this expression where you can see instead of cos cube, we have cos 3 omega c as well, which is a high frequency carrier. So just to give you an idea where it's coming from, so cos cube can be written as cos omega ct into cos square omega ct. So this cos square omega ct can be written again through the same trigonometric identity that we saw previously. It can be written like this. And so when we take this cos omega ct common in this way, we are left with this expression. So in this expression, we can filter out the desired signal through a bandpass filter, but that signal still has this component, which is the undesired component. This one is the desired component, but we also have this undesired component, which is dependent upon the time. It's a time varying component. So this causes distortion in an AM signal. So that means an amplitude modulated signal will be distorted if it's passed through a nonlinear device. So immunity from nonlinearity is the primary reason for use of angle modulation in microwave radio relay systems. So we need radio relay systems between two transmitter and receivers in order to amplify the signal. So generally we use highly efficient nonlinear class C amplifiers because they are high power amplifiers, since their response is nonlinear. So FM or angle modulated signal is the most suitable modulation type to use in this case. So the effect of amplitude variations caused by rapid fading can be eliminated by using automatic gain and bandpass limiting. So in this case, if we are using an FM signal, we can avoid the fading, that is the cause due to the channel. We can use an automatic gain control and bandpass limiting in order to fix the amplitude in order to make the amplitude of the FM signal constant. So these were the main advantages that made FM attractive for especially the 1G, the first cellular phone systems. So now the systems are much more complex. They are, in fact, a combination of different modulation formats and multiplexing techniques. So the second major type of impairment that is caused on a signal is the interference. So we'll see what is the effect of interference on an angle modulated signal. So we'll see it's also less vulnerable than amplitude modulated signal to small interferences. So angle modulation is less vulnerable. So let's say in order to quantify this, let's say we have an unmodulated carrier. It has an interference with this signal. So this I cos omega ct plus omega t is the interfering signal. And generally, the interfering signal that is close to the carrier frequency causes more problems. So at the receiver side, we will get this signal, the desired one, and then we will also get an interference signal. So the sum of the two will be obtained at the receiver. After we open this term using trigonometric identity and taking out cos omega ct as common, we get this expression. So here we can see we have two types of terms. So one is the quadrature term, and this one is the in-phase term. So using trigonometric identity, we know we can reduce this expression to this one, where the ERT represents the magnitude of this carrier, and phi dt is the phase. So it depends. Phi dt can be obtained through this using the trigonometric identity tangent inverse. The quadrature component appears in the numerator, and the in-phase component appears in the denominator. So this is phi dt. Now, this is the expression we obtain of the received signal. Now, let's study this received signal. We can see if the interfering signal is small, that means the interfering amplitude I is much, much smaller than the desired signal amplitude. So this term can then be ignored in the expression, and we are left with only this expression for the phase angle of the combined signal at the receiver. So remember, the desired signal is only this one, cos omega ct. So this phase angle is completely an undesired quantity. So we want it to be negligible or zero ideally, right? So the phase of this term, which is the received signal, is phi dt, which as we said, it's the undesired phase. Its instantaneous frequency would be, if we take the derivative of the phase, we will get this instantaneous frequency where phi dt now has a dot above it, which represents the derivative. So if this signal, the received signal, is applied to an ideal phase demodulator, let's say we pass it through a phase demodulator, what is the output we get? We will get the phase of the signal. So this would be the output, which is again an undesired output. Similarly, if this signal is passed through an ideal frequency demodulator, then we would get the derivative of this term at the output of the frequency demodulator. So the output for PM is equal to phi dt, which if we look at the expression, this one is equal to this. The output of a frequency demodulator is the derivative of phi dt, so which would be the derivative of this term, the sinusoidal term, and that's how for FM we get this as the output, right? So these are the undesired outputs, and they are obtained as a result of this term I, interference term. So if you make this I is equal to 0, that means if there is no interference, these outputs would be 0. So the undesired outputs would be 0. So another thing we can see is the interference. This y dt is inversely proportional to the amplitude A of the carrier. So if we want to reduce the effect of interference, we can use a high power signal, and the interference effect would be quite small. So this is different from the AM signals because the interference output is independent of the carrier amplitude in case of AM, but in case of angle modulation, we see the interference is inversely proportional to the amplitude of the carrier. So that's why angle modulated systems are much better than AM systems at suppressing weak interferences. So if we plot these interference on y-axis against the frequency, against the omega, the radian frequency, we get a plot like this. So for FM, the interference increases as we increase omega. So it increases linearly. So this can be seen from this expression where we see there is an omega in the amplitude. So as this omega is increased, the interference y dt increases. For PM, we can see that if we increase omega, for all the values of omega, the interference amplitude remains constant, because if we look at this expression, the amplitude is independent of the frequency. So these are the two responses, FM and PM. So these are the interference amplitude with respect to omega. So as we'll see in another video, we will use pre-M phases and DM phases circuits to tailor the interference induced on an angle modulated signal, but that is discussed in another video. So in this video, we have only discussed the type of distortions that can be introduced on FM and AM signals and what is the effect of those distortions. We have seen that.